Let's start with a problem that feels incredibly human, but is actually a massive headache for computers. Meaning.
Right.
And I don't mean the meaning of life, I mean the real nuts and bolts of it. If I say the bank is closed and then the river is overflowing, you instantly know those are two different kinds of bank. You don't even think about it.
But a computer, for a long time, just saw a string of four letters. B-A-N-K. That's it.
Exactly. And that gap, the one between just matching keywords and actually understanding semantic relatedness, that's the whole game in AI, isn't it?
It's a huge part of it, yeah. It's what powers everything we use. Information retrieval, so search engines, spell checking, text categorization, all of it. If the computer doesn't get that doctor and hospital are related, even if they aren't synonyms, everything breaks.
Which is why today we're doing a deep dive into this paper from the Technische Universität Darmstadt. It's titled, and it's a mouthful, Combining Heterogeneous Knowledge Resources for Improved Distributional Semantic Models.
It's from 2011 by Georgi Sarvis and his team.
And before you tune out because of a word like heterogeneous, just stick with us. Because the mission today is basically to solve a mystery. How do you get a computer to read an encyclopedia, a dictionary, and a thesaurus all at once and come out smarter than if it had just read any one of them alone?
I like to think of it as the Avengers strategy for artificial intelligence.
The Avengers strategy. How so?
Well, each hero is strong, right?
Yeah.
But they have massive blind spots. You need the whole team. Before this paper, most researchers were trying to build these semantic models with just one hero.
And that hero was Wikipedia?
Almost always Wikipedia, which, it makes sense. It's huge.
She's got everything.
It's got a lot of facts. But the paper argues, and this is the big idea, that relying only on Wikipedia is dangerous. It creates a lopsided intelligence. You need different types of knowledge to fix those blind spots.
Okay, so let's break that down. Before this paper drops in 2011, what was the status quo? How was the AI actually, reading Wikipedia?
The main method was called explicit semantic analysis, or ESA. And it's a really brilliant concept, actually.
Okay.
ESA treats every single article in Wikipedia as its own concept. So just imagine a massive spreadsheet. Along the top, you have a column for every article. The moon, economy, Michael Jordan, cheese, millions of them.
Got it. A huge spreadsheet.
Now, take a word you want the computer to understand. Let's use jaguar. The computer scans all of Wikipedia and asks, how often does the word jaguar appear in each of these articles?
Okay, so it'll pop up a lot in the article for the animal, of course, and probably Amazon rainforest, but then also in cars, luxury, maybe British engineering.
Precisely. And you get a list of scores for each article. That list, that whole row of numbers, is the concept vector. It's a mathematical fingerprint for the word jaguar based on the company it keeps.
So if you want to see if Jaguar is related to Porsche, you just compare their fingerprints.
You compare their vectors, and since they both hang out in the car and lingerie articles, the math says, yep, highly related.
That sounds pretty solid. It's learning by association.
It is, but here's the trap. Wikipedia is an encyclopedia. It's full of nouns. It describes things, people, events, places.
Okay.
What happens when you ask it to understand a verb? Something like run.
Run. I mean, it's probably in almost every article, right? He ran for office, the river runs deep, the program runs on Windows.
Exactly. It's everywhere,
Right.
which means its concept vector is just a total mess. It's blurry. It has no distinct fingerprint.
Ah.
Wikipedia is great for world knowledge, knowing that Einstein links to relativity, but it's terrible for lexical knowledge, like knowing run is similar to sprint or jog.
It's like trying to learn what the word run means by only reading a history textbook. You see the word used all the time, but you never get the actual definition. The nuance is lost.
That is the perfect analogy. And that's where the heterogeneous part of the title kicks in. The researchers said, why are we only giving the computer the history book? Let's give it the dictionary too.
So this wasn't about adding more data of the same kind. It was about adding different kinds of knowledge.
Right. They combined three specific resources. First, you have Wikipedia for that broad encyclopedic knowledge.
Okay.
Second, WordNet.
That's the classic, right? The one linguist built by hand.
Yep, a lexical database.
Hmm.
It knows a dog is a type of canine. That hot is the opposite of cold. It's very structured, very precise, but it's small. It has no idea who Lady Gaga is.
And the third one,
Wiktionary,
the crowdsourced dictionary.
which is kind of the perfect bridge between the two. It has the structure of a dictionary with definitions and synonyms, but because it's a wiki, it's constantly updated. It has the slang, the pop culture. It sits right in the middle.
Okay, so we have the encyclopedia, the linguist's database, and the crowd's dictionary. Now, this is the part that sounds like information overload. How do you actually combine them? You can't just staple the pages together.
No, you can't. This is where the machine learning kicks in. They built a system that learns when to trust which resource.
So it's not just averaging the scores from all three.
No, that would be naive.
Hmm.
Think of it like a panel of judges. You've got Judge Wikipedia, Judge WordNet, and Judge Wiktionary. You show them the word pear, Einstein, and physics.
Okay.
Judge Wikipedia goes crazy. 10 out of 10. Highly related. But Judge WordNet just shrugs and says, I don't know who Einstein is. That's a proper noun. 0 for me.
And if you average those scores, you get a mediocre result, which is just wrong.
Exactly. So you need a system, a manager, that says, wait, for proper names like this, I need to listen to Judge Wikipedia. I'm going to turn down the volume on Judge WordNet. They use things like linear regression and multi-layer perceptrons to learn those weights automatically.
So it learns the bias of each source.
It learns the reliability of each source depending on the context. It figures out, okay, for verbs, I should really trust WordNet. For new brand names, Wikipedia is my guy.
That makes a lot of sense. But I saw in the paper they spent a lot of time on this idea of pruning.
Yeah.
And they were very proud that they didn't have to do it. Why is that such a big deal?
Okay, this gets a little technical, but it's a really important innovation. Remember that concept vector, that long list of scores from Wikipedia articles?
The fingerprint.
Right. In the old way of doing things, that vector was full of noise. The word bank might show up, once in an article about penguins just by accident. It's meaningless noise.
So researchers will just clean it up manually.
They'd prune it. They'd set a rule like, okay, delete any value below 0.05 or only keep the top 1,000 scores.
But that feels so arbitrary.
It's completely arbitrary. It's a magic number that you, the researcher, have to guess. And if you guess wrong, you might be throwing away really important information.
It's like trying to tune up the static on an old radio. If you turn the knob too far, you lose the music along with the static.
That's a great way to put it. This paper proposed a specific mathematical setup using a function called avgprod with some logarithmic weights that elegantly solves this. The math itself naturally suppresses the noise. The static just fades away without you ever touching a knob.
So no more magic numbers.
No magic numbers. No guessing. You feed the raw data in, and the model handles the noise. And that makes it way more robust, especially when you apply it across different languages, because you don't need a human to hand-tune the static knob for German versus English versus Spanish.
Which is good because I think they tested this on 5 languages.
They did.
Yeah.
English, German, Arabic, Romanian, and Spanish. And the results were consistent.
Okay, let's get to it then. The results. Did the Avengers strategy actually win?
It won significantly. Especially in the areas where the single models were weakest, the biggest victory was with verbs.
The run versus sprint problem.
Exactly. They used a standard data set that's all verb pairs.
Yeah.
The Wikipedia-only model was, mediocre at best. But the combined model saw this huge jump in performance. It was clear proof that WordNet and Wiktionary were filling that lexical gap we talked about.
And what about those standardized test questions, like pick the synonym for fast?
That's a great test because it measures 2 things at once, accuracy and coverage. You can't get the right answer if you've never even heard of the word.
And I'm guessing Wikipedia misses some dictionary words, while WordNet is missing all the modern stuff.
Precisely. By combining them, the coverage, the number of words the system even recognized, went way up. And for English, the harmonic mean, which is a score that balances accuracy and coverage, improved by more than 0.10.
Now, 0.10 might not sound like a lot to a layperson.
In this world, an improvement of 0.10 on a benchmark is like jumping a full letter grade.
Yeah.
It's the difference between a system that feels clunky and one that starts to feel genuinely smart.
So we've covered single words, but real language is about sentences, documents. Did they try to apply this to bigger chunks of text?
They did, yeah. They look at 2 things, semantic relations and text similarity.
Semantic relations, is that like analogies?
Sort of. It's about categorizing the type of link between words. It's one thing to know bird and nest are related. It's another level to know the relationship is entity origin, or that wine and bottle is content container.
And the combined model was better at that.
Significantly better. Adding their combined score as a feature to a baseline classifier made it much better at correctly labeling those relationships.
Okay, and text similarity. That sounds incredibly complex. If I have 2 documents, each with 1,000 words, do I have to compare every single word to every other word? That's a million comparisons.
That's the computational nightmare, yeah. But because they have these concept vectors, they can use a really clever trick called the centroid.
The centroid.
Think of it like a center of gravity. Imagine you could plot every word in a document on a big 3D map of meaning. If you average all their positions, you'll get one single point right in the middle of that word cloud.
Okay.
That single point is the centroid. It represents the overall meaning of the entire document in just one vector.
So wait, instead of comparing 1,000 words to 1,000 words, you just compare one point to one other point.
Exactly. It's lightning fast.
Yeah.
And because the underlying words, the atoms of that cloud, were powered by the stronger combined model, the centroid vector was much more accurate. It really captured the document's essence.
That's a huge deal for search engines. It means they can see that a document about felines is relevant to your query about cats without needing an exact word match and without taking forever to calculate it.
Speed and accuracy. That's the holy grail.
So bringing this all together, what we have here is a paper from 2011 that was essentially yelling, stop looking at the world through a single straw.
That really is the core takeaway. Knowledge is most valuable when it's diverse. The way we define a word in a dictionary is different from how we describe it in an encyclopedia.
And an AI that wants to understand human language needs all of that.
It needs the full spectrum. It's the complementarity of these different resources that drives the performance. Wikipedia gives you the nouns, the names, WordNet gives you the verbs, the structure, and Wiktionary helps fill in the gaps between them.
So what does this all mean for us? It feels like the path to smarter AI isn't just about feeding it more data, but about feeding it different kinds of data that can work together.
Exactly. It's about a balanced information diet. Turns out computers need one too.
Which leaves me with a final thought. If computers make better, more nuanced decisions when they consult the encyclopedia, the dictionary, and the thesaurus all at once, maybe there's a lesson in there for how we humans form our own opinions.
That's a great thought to end on.
Well, on that note, we'll wrap up this deep dive. Hopefully, the next time you use a search engine and get a startlingly good result, you'll have a better idea of the invisible team of resources working together in the background. Thanks for listening.
Thanks, everyone.
We'll catch you on the next one.